The relativistic universe overturns our familiar world through three uncanny features: length contraction, time dilation, and especially, the relativity of simultaneity. To see how length contraction comes about, let us consider two identical circular rings that briefly change color at identical regular intervals and move relative to each other at constant velocity. At low relative speed, the two rings flash simultaneously. But for relativistic speeds, we might expect something like this. If the moving ring shrinks by a factor of 2 in the direction of motion, then the rate at which it flashes slows down by a factor of 2. However, this picture is incorrect because it does not account for relativity of simultaneity. What we see instead are pairs of point-like flashes occurring at time-dilated intervals and progressing along the moving ring in the direction of motion, starting from the rearmost point. The simultaneous lighting up of the moving ring is no longer perceived as a simultaneous lighting up from the stationary ring, and conversely. Stranger yet, the path of each pair of flashes, as seen from the ring at rest, is an ellipse, not contracted, but elongated, along the direction of motion, by a factor identical to the factor of time dilation. So, how does this fit in with the length contraction of the moving ring? The moving ring appears to undergo length contraction because it is seen in a veritable space-time cross-section across a finite length of its proper time. The space-time cross-section slices through the collection of elongated paths, so that visible flashes are always aligned along a uniformly moving ellipse, length contracted along the direction of motion. This effect is independent of both the distance between the two rings and the time it takes a light beam to travel between them. It is simply a consequence of the way coordinates of space-time events change between the moving and stationary frames, according to the relativistic Lorentz transformations.